right, example 2. So I've already written this down. It says to verify Stokes' theorem, if your surface is z equals 4 minus x squared minus y squared, the parabola opening down, and your vector field is 2z, x, and y squared, okay? And it says the part of this that lies above the xy plane. Okay, so your boundary curve is going to be this curve, this circle in the xy plane with a radius of 2. And it's going in this direction, which is important because you have to think of the right-hand rule. So if it's going around this way, sorry, that's not videoing very well, your thumb would be pointing up. So the positive orientation is always up. If it went the opposite way, our answer would just be negative, or the opposite of whatever we get. Okay. So verify Stokes' theorem. Again, Stokes' theorem says f dotted with dr is equal to the double integral of the curl of f dotted with your ds. Okay. So first I'm going to do this one. F dotted with dr. So I have to parametrize this curve. To parametrize this curve, x is equal to 2 cosine theta, y is equal to 2 sine theta, and z is equal to 0. Okay, so r of theta would be 2 cosine theta, 2 sine theta, 0. Okay, r prime of theta would be negative 2 sine theta, 2 cosine theta, and 0. Okay, so when we calculate this, we have f, which is 2z x y squared, add with r prime of theta, negative 2 sine theta, 2 cosine theta, and 0. This will be d theta. Theta goes from 0 to 2 pi. We're just going around this curve. Notice on this curve, r is always equal to 2. Okay? So we don't have r as one of our parameters. And it's a single integral, so we shouldn't. Okay, so 0 to 2 pi. 2z, well, z is 0. So 2z is 0. X is 2 cosine theta. Y squared is going to be 4 sine squared theta. Dotted with negative 2 sine theta, 2 cosine theta, and 0 d theta. Multiplying this out, we get 0 plus 4 cosine squared theta. And then we get plus 0, so d theta, 0 to 2 pi. Okay, remember how to calculate this. We're going to use the formula for cosine, or the identity, 2 cosine 2 theta, which is equal to 2 cosine theta minus 1. 2 cosine squared theta minus 1, so cosine squared theta equals cosine 2 theta plus 1 over 2. Okay. We want 4 cosine squared theta, so 4 cosine squared theta is going to be equal to, multiply by 4, 2 cosine 2 theta plus 2. So we want to evaluate, integrate 0 to 2 pi of 2 cosine of 2 theta plus 2 d theta. Antiderivative of this would be sine of 2 theta, just sine of 2 theta, right, plus 2 theta. Going from 0 to 2 pi, plugging in 2 pi, you're going to get sine of 4 pi, which is 0. Here we get 4 pi, and then plugging in 0, you're going to get 0. So 4 pi is our answer. So that wasn't too bad. Okay. Now let's do it the other way. Okay. So the other way that we want to do this problem, notice what we did here. We did the line integral. Now we're going to do the double integral of the curl. Okay. So we're going to do the double integral of the curl of f dotted with ds over this surface where z equals 4 minus x squared minus y squared. Okay. And the vector field is this. So the curl of f is equal to I, j, k, d dx, d dy, d dz. Okay, and then we've got to z, x, and y squared from our vector field. So the curl of f equals 2y minus 0. The j direction, we've got this minus this, so that would be -2, but it's the j, so it's positive. And then the k, we're going to get 1, just 1. Okay, so the curl of f dotted with this, our curl of f is 2y comma 2 comma 1. Now remember, since z is a function of x and y, this thing becomes opposite dz dx. So dz dx is -2x. That becomes a positive 2x. Opposite dz dy, so 2y, and 1. And then dy dx. And again, that's another integral. Okay? So let's do the dot product, and we get 4xy plus 4y plus 1 dy dx. Now notice what we're doing here. Here we're not just on the, we have to project this surface onto the xy plane. And when we do that, we get the same circle. But we're not just on the boundary of the circle, we're actually throughout the entire circle. So if we want to use polar coordinates here, the x is going to be r cosine theta, y is going to be r sine theta, and we're going to have to multiply this out. So that's going to be 4r squared cosine theta sine theta plus 4r sine theta plus 1 r dr d theta. Okay. So see that 4. Okay, now I'm going to multiply the r into all of these. So we get 4r cubed cosine theta sine theta plus 4r squared sine theta plus r dr d theta. Okay. And r goes from 0 to 2. Theta goes from 0 to 2 pi. So integrating with respect to r, we're going to get 4r to the 4th over 4. So that's just r to the 4th cosine theta sine theta plus 4r cubed over 3 sine theta plus r squared over 2. Evaluating from 0 to 2, it's going to be 16 cosine theta sine theta plus 8 times 4, 32 over 3 sine theta plus 2 minus, and then we plug in 0. We're going to get 0 for everything. Okay, so now we integrate from 0 to 2 pi, 16 cosine theta sine theta plus 32 over 3 sine theta plus 2, subtract the theta. So this becomes 8 sine squared theta. Let's double check that. That's going to be 8. Yep, that's right. Plus minus 32 over 3 cosine theta plus 2 theta from 0 to 2 pi. Okay, plugging in 2 pi, we're going to get 0. Cosine 2 pi is 1, so minus 32 over 3 plus 4 pi minus, now plug in the 0, 0 minus 32 over 3 plus 0. Okay, this one and this one cancel, and you get 4 pi. Okay, which is the same thing we got when we did it the other way. Okay, so here we evaluated the curl of f done with your ds over the entire surface. Okay, we got 4 pi. And what we did first was this, the integral of f dot dr on the boundary curve. Okay. Now, another reason this is really useful, so this was kind of a pain to evaluate this double integral of the curl of f dotted with ds. Okay? We could have picked another surface. If we wanted, we could have chosen a different surface that has the same boundary curve. We could have simply picked the surface of this disk on the xy plane and done this integral over that surface instead. Stokes' theorem tells us that it should be equal. So this will be equal to any other surface integral flux of the curl through that surface, as long as they have the same boundary curve. Right? We wouldn't have actually verified Stokes' theorem, so we had to do it directly what was told to us. But if they say use Stokes' theorem, we could have picked a different surface that made this easier, as long as that different surface we pick has the same boundary curve. So it gives you some options. It allows you some flexibility to maybe do some easier calculations and do something that's possible when it's not possible to do another way.